world-famous authority on aerospace sciences. It showcases a person who has performed notably and distinguished himself technically in the field of astronautics, and tonight's lecturer has done just that. Dr. Vigor is a fellow of AIAA, ASME, the Royal Aeronautical Society, and is one of the most prominent figures in propulsion, combustion, and energetics. Dr. Yang received his PhD from the California Institute of Technology in 1984. Following 1 year as research fellow in jet propulsion at Caltech, he joined the Pennsylvania State University in August of 1985, becoming the John L. and Genevieve H. McCain Chair in Engineering in 2006. He began his tenure in January 2009 as the William R. T. Oakes Professor and Chair of the Daniel Guggenheim School of Aerospace Engineering at the Georgia Institute of Technology. Dr. Yang has taught undergraduate and graduate courses in thermodynamics, fluid mechanics, heat transfer, propulsion, combustion, and mathematics. He has also delivered numerous professional short courses and lectures on non-steady combustion and flow dynamics in propulsion and power generation systems. Dr. Yang's research encompasses a wide spectrum of topics, including combustion instabilities in propulsion and power generation systems, chemically reacting flows in air breathing and rocket engines, and nanotechnologies for propulsion and energetic applications, to name just a few. He is established as principal or co-principal investigator over 65 research projects, including 9 DoD MURI projects, and has been awarded more than $32.5 million to date in research funding. Dr. Yang's research findings are described in 170 archival journal papers, which include 10 comprehensive reviews, and over 200 conference papers. He has published 11 books and 6 dedicated journal issues in the area of propulsion, combustion, and energetics. Dr. Yang's contributions have been recognized with awards from several national and international professional societies, including the ASME 2014 Worcester Reed Warner Medal, AIAA's 2008 Pendry Aerospace Literature Award, AIAA's 2005 Air Breathing Propulsion Award, and the Pennsylvania State University Engineering Society 2005 Premier Research Award. During tonight's lecture, he will speak to us about the basic research and innovative technology that will be required to address one of today's grand challenges in astronautics, that is space propulsion. Dr. Yang.
Thank you very much. Thank you very much. I'm very honored and humbled being here and sharing my thoughts on space propulsion. Probably you have noticed that there are 3 photo images on the screen. The first one is Saturn V, a launch vehicle. And on the right, there's a space shuttle. On the left, there's NASA's SLS, which stands for Space Launch System. Yes. Well, human space activity commenced in 1957 when the Russians delivered their first spacecraft into the Earth orbit. And ever since then, enormous progress has been made. For example, the first Mars mission, flyby mission, was conducted in 1965. And in 1969, Neil Armstrong landed the moon. And in 1981, that's the first space shuttle flight by my dear friend John Young and Robert Crippen. And then all the way through 2011, including 135 space shuttle missions. Now we are in the deep space exploration time, and for example, Curiosity rover landed on the Mars in 2012. So tremendous progress has been made in the past 60 years. In terms of rocket propulsion, how many rocket engines developed in the past 60 years? Well, this table shows the time evolution of a flight engine developed in the United States from 1955 through 2006. Combined, there are 32 new flight engines and their derivatives developed in the US. There are several messages that I'd like to convey to you. Number one is, when we look at rocket engine development, the prime time is in the 1950s and the 1960s. During those time period, there are 13 rocket engines developed. For example, in the space race time period, there are 9 engines developed. Then for Apollo project, there are 6 rocket engines developed, including the famous Legacy F1 J2, lunar module descent engine and a lunar module ascent engine, and so forth. For space shuttle time period, 3 primary liquid rocket engines developed. That include a space shuttle main engine, orbital maneuver engine, and a reaction control engine, plus the famous mighty solid rocket booster. So that's the prime time for rocket engine development. Then after that, the situation became a little bit depressing. For almost 40 years, very limited rocket engines developed in the United States. And it's a really, a very, very depressing time period. Then the situation has become a little bit different. 2006, the first commercially developed rocket engine were put in the market. That's RS-68. Essentially, that's an enlarged engine derived from J2 rocket engine, and it's commercially developed by Rocketdyne. And these days, we are talking about several new engine development. That includes Aerojet Rocketdyne's AR-1, Blue Origin's BE-4, and SpaceX's Raptor engine. So this is the situation in the United States. The next chart that I'd like to share with you is the time evolution of all the engine development programs, not just for flight engine, but also for test and development engines in the United States. And there are 2 charts. One is for solid rockets, the other one is for liquid rockets. And again, there are several messages that I'd like to share with you. When we look at those engine development programs, we notice that many of those programs are short-lived. Very, very short-lived. So in other words, they first establish those programs, and then they cancel those programs for various reasons. That's number one. Number 2 is for flight engines, typically that took 5 to 10 years to develop a flight engine. Number 3, as I already mentioned, for almost 40 years' time, there were very limited rocket engine developed. So this is the situation in the United States. Well, let's go back to the history. Taking Apollo Saturn V launch vehicle as an example. This is a mighty rocket vehicle, and there are several stages. Stage 1, there are 5 F1 engines, and each engine delivered almost 1.5 million pound force. So combined, we have 5 F1 engines for the stage 1 of a Saturn V launch vehicle. The lift-off thrust is a 7.5 million pound force. That's about 30 Boeing 747 takeoff thrust. So it's a tremendous. Stage 2, there are 5 J2 rockets, each delivered almost 200,000 pound force. And stage 3, there's only 1 J2 engine. And also there are a number of in-space propulsion systems, including lunar module descent engines and so forth. So this is for the Saturn V launch vehicle. So in short summary, there are 6 different engines developed, including F1 J2 all the way to reaction control engines such as R4, D, and C. And those engines covered a very broad range of thrust from 100 to almost 1.75 million pound force. So this is the situation with Apollo. Well, what happens is, when John F. Kennedy made his famous speech in front of the Congress in 1961, he said, within 1 decade, we want to send a man onto the moon and return that person safely back to the Earth. So that's JFK's vision at that time. But what about the propulsion system? Well, this is the situation at that time. NASA and Rocketdyne, they realized to develop such a mighty propulsion system is very challenging, but it's pretty much doable. So what they did at that time is they basically enlarge, scale up H1 rocket engine to make it F1. And also for J2, they basically use RL-10 as the technology basis to scale up to make a J2 engine. This is the situation at that time. But the situation is not, was not that smooth. What happens is, when Rocketdyne engineers develop their test engine, they put everything on the test stand. also at the same time, they measure the pressure time history. They encountered a very severe problem. Let's pay attention to the scale on the chart. Each scale represents 5,000 psi. So in other words, this test engine experienced a tremendous pressure oscillation in the chamber with a peak-to-peak amplitude around 10,000 psi. As a consequence of that, the test engine burned out in few seconds. This is a test engine, and taking an injector faceplate as an example, it's made of a 10-inch stainless steel. So for such a thick metal piece, it burned out in few seconds. So it pretty much tells us the magnitude of the problem and the challenges people faced at that time. Well, this is a sample of a damaged combustion chamber. This is not from F1 engine, but from a very similar combustion device people tested at that time. How to solve this problem? The president gave NASA and the industry 10 years' time to establish this Apollo project. In terms of the propulsion system development, they essentially had only 4 years' time. So within 4 years' time, they have to develop such a wide range of propulsion systems. So NASA and the industry did is they practically tried every kind of injector systems. So in other words, so long as you have an idea, they were willing to try and also put that on the test stand. This is a summary of the injector patterns people considered at that time. And well, this picture shows the water flow test of a F1 engine. The mass flow rate is nearly 6,000 pound mass per second, and this really shows the magnitude of the problem people faced at that time. Also at the same time, okay, people try to use all kinds of passive damping devices to suppress unsteady motions in the chamber. For example, okay, they use baffle blades to suppress unsteady motions, especially in the transverse direction. Baffle blades are a mechanical piece protruding into the combustion chamber. And they started with a 3 baffle compartment design all the way down to 81 baffle compartment design as shown at the lower right corner. Of course, this 81 baffle compartment design was not a wonderful idea, but it also shows how desperate people were at that time. As I said, so long as you had an idea at that time, they were willing to try and put it on the test stand. This 81 baffle compartment design, that combustion device burned out just in few seconds, and very unfortunately. Finally, okay, after many full-scale test firings and redesigns and troubleshooting, they were able to achieve a stable combustor, as shown down here. Well, question is this, how much effort people put in at that time? In order to get a stable rocket engine at that time, Rocketdyne and NASA established a project called Project First. The Project First was divided into 3 different time periods. The first one is a PFRT stage. It's a preliminary flight rating test. It covered a time span of only 9 months, ranging from October 62 all the way to June 63, only 9 months. And the number of full-scale tests is 207. Stage 2 is a flight rating test, FRT. It covers a time period from June 63 all the way through January 65. Then finally, they had a flight qualification test, FQT. And combined, okay, a total of 1,332 full-scale tests and more than 337 component tests with 108 injector designs. So that's how we were able to get a stable F1 engine. So a very serious question is how much money people spend on F1 engine. This is a number. Nobody really knows how much money we spend on F1 engine, but we did a rather reliable analysis. This is a number that we obtained. For F1 engine, people spend $2.4 billion. That's the money in 1966. It's equivalent to 17.85 billion in today's money. For J2, people spent $1.7 billion in 1966. That's equivalent to $12.65 billion in today's money. So if we have to redo F1 and J2 engine today, that's almost a Tom Cruise, so-called Mission Impossible. Yes. And that's one example. The next example that I'd like to share with you is a space shuttle. Space shuttle is a mighty device. It's a wonderful, tremendous accomplishment. In terms of a propulsion system, there are several highlights. First one, of course, is the space shuttle main engine. On the orbiter, there are 3 different types of propulsion systems: space shuttle main engine, orbital maneuver engine, and the reaction control system engine. Those are 3. And also, people developed the biggest solid rocket motor ever at that time, which is a 4-segment rocket motor. Each delivered almost a 3 million pound force. It's equivalent to the thrust of 2 F1 engine and so forth. So this is for space shuttle. Then again, how much money people spend on the propulsion system. This is the cost of SSME. Well, it's a $2.45 billion in 1980s money. That translates to $7.7 billion in today's money. So that's the cost for us to develop a SSME engine. Although the engine itself is so wonderful, so powerful, but the cost has become really unaffordable these days. So that's the situation. Well, this one shows the cost and the test histories of those 3 legacy engines. Taking F1 as an example, as I already said, folks spent $2.4 billion in 1966 money, and the number of rework cycles is 203. So in other words, the average cost for each rework meaning redesign, retest, that is $9 million at that time. And it's equivalent to 67 million in today's money. So in other words, if we can reduce the number of reworks, then we can substantially reduce the development cost. And this is something that we have to keep in mind. And the same thing applied to J2 and SSME engines. So yeah. Now, back to today, 2016. Several years ago, President Obama shared his vision with the entire nation. He said, by 2025, we want to send mankind to a remote place. It's much beyond the moon. That's his vision. And also by 2035, we want to send mankind to orbit Mars and return those people safely back to the Earth by 2035. And again, this is a very, very ambitious goal, yes? Well, this one shows, NASA's vision. And essentially, there are 3 different places for us to go. Near the Earth is almost commercial and military space. That's, yes, of course, we still need the ISS, International Space Station, as a basis for deep space transportation and exploration. Then the next one is we want to go to a place, a destination, which is much beyond the moon. Then we are talking about a flight distance of hundreds, thousands miles, and that requires another major launch vehicle, so-called SLS Block 1. SLS Block 1 can handle a payload up to 70 tons, metric tons. That's the second destination. The third destination is by 2035, we are able to travel to Mars. Then we are talking about a flight distance of tens of millions of miles. And it's not an easy trip for human to go. Yes. Well, then what about those opportunities and the challenges for propulsion systems? Essentially, we have to consider 2 different kinds of propulsion systems. The first one is launch propulsion. The second one is the in-space propulsion. The launch propulsion, the primary goal is to make access to space more reliable, more routine, and more affordable. So affordability is a #1 issue for us to be concerned with. That's for our launch propulsion system. Well, how to accomplish that? As usual, we have several propulsion options for launch propulsion systems. First one is a solid rockets. Second one is a liquid rockets. People are also considering air-breathing propulsion systems and other unconventional systems and so forth. Let's talk about those options one by one. For solid rocket motors, the state-of-the-art is a shuttle-derived solid rocket motor, which has 5 segments as shown down here. And well, this is a mighty device, and it can deliver a thrust almost 3.6 million pound force, 3.6 million. It's a tremendous. And the propellant weight is a 1.4 million pound mass, and so forth. Is it good, or can we do better? Well, the answer is yes, we probably can do better, probably much better down the road. Here are the important issues. I have to say that, okay, Orbital and ATK and the NASA Marshall, they really have done a tremendous job. It's a great job they did. But looking to the future, there are a few things that we probably can do even better. First one is propellants. Let's look at the propellant composition. Current propellant for space shuttle or shuttle-derived systems using ammonium perchlorate is AP, combined with aluminum particles, and HTPB, PBAN is a polymer as a fuel binder. The composition is 70, 16, 12, and 2% by mass. Is it good? Well, it's okay, because a PBAN is a propellant which is pretty old, even older than I am, although I myself is already pretty old, yes. And the ISP is 242 seconds. It's fine. And if we can replace the PBAN by HTPB, then we probably can substantially increase the ISP from 268 seconds in vacuum to almost 300 seconds in vacuum. So now you see the big payoff. If we switch from PBAN to HTPB, it's another polymer. But I have to say that HTPB is not a new product. Folks have been using HTPB for almost 40 years. So this shows this community really needs to be energized from the technology perspective, not necessarily from engineering perspective, but certainly from the propulsion perspective, this community needs to be energized. So that's the first issue. The second issue is ammonium perchlorate. Each solid rocket motor carries almost 1 million pound ammonium perchlorate. It's very toxic. When you look at the combustion products of ammonium perchlorate, hydrogen chloride is extremely corrosive and toxic. So that's the number 2 issue. Number 3 issue is the propellants contains a big fraction of aluminum particles with a particle size in the range of 5 to 100 microns. And the purpose is to suppress unsteady motions, instabilities. The second reason is to add energy density. But the problem is when we burn those micron-sized aluminum particles in a rocket motor environment, the combustion efficiency is just not there because of agglomeration and other issues. So that's another opportunity for technology improvement. And finally, okay, I have to say that the current case is a metal case. It's a little bit heavy, so the trend is moved to composite case to reduce the weight and also at the same time to reduce the overall system reliability. So those are the issues for solid rocket motors if we choose to continue using solid rocket motors. Then what about liquid propulsion? Well, liquid propulsion, and again, the issue is cost. Make it very, very affordable. Then how to accomplish that? It's very, very clear that for future space transportation, for booster engines, 1, it has to be staged combustion cycle engine, and 2, kerosene or hydrocarbons such as methane ought to be considered for very, very good reasons. And what is a stage combustion cycle engine? Well, space combustion cycle engine means, okay, those propellants, the two propellants, the oxidizer and the fuel, they were burned in two stages. Stage one in the preburner, the purpose is partially burn the propellants and using the combustion products to drive turbopump. That's a stage one. And then stage two is a main combustion chamber. So there are many, many benefits of doing that. But the primary benefit of a stage combustion cycle engine is ISP is almost 10% greater than gas generator cycle engine. And also the energy density is much higher than hydrogen propellant. So those are the advantages. Then the next thing is, okay, what is the most effective way for us to develop a stage combustion cycle engine? And I have to say that in terms of a technology, this is by no means a new technology. Folks have developed a stage combustion cycle engine for almost 50 years. When we look at this diagram, it shows the first stage combustion cycle engine was developed in Russia in 1960s. In 1960s, then over time, colleagues in Russia and the former Soviet Union, they have developed a 65 stage combustion cycle engine. Of those 65 stage combustion engines, 26 are flight engines. In the US, there's only one stage combustion cycle engine. That's a space shuttle main engine. We have only one versus 65. So that tells the situation. But the good news is these days, 3 engine companies have decided to develop the next generation stage combustion cycle engine. For example, Aerojet Rocketdyne, they are developing a kerosene oxygen-based stage combustion cycle engine, so-called AR1. Blue Origin, their engine destination is BE4. It's using liquid oxygen and methane. That's a stage combustion cycle engine. And at the same time, SpaceX is developing Raptor. Raptor is a full flow stage combustion cycle engine using oxygen and methane as propellants. So we are getting there. But then the question is this, how to do it? We have 2 practical constraints. One, we have to develop those engines in time and within the budget. So question number 1 is how much budget available for developing those engines? Second thing is how much time available for developing those engines. So those are the practical issues. And I have to say that the single important challenge facing the development of a launch propulsion system is the cost and the time and the rate of production. It's not a technology issue, because the technology has been demonstrated for 50 years, and the real opportunities for us is on the cost reduction and the rate of production side. So those are the 2 things we should always keep in mind. Well, this figure shows the engine development cost breakdown. Essentially, okay, initial design is 2% of the overall cost. Engineering, throughout the entire program, 15%. But we spend 75% of the resource on redesign, testing, and redesign. So in other words, okay, this is a very traditional design, test, fail mode. And this kind of a cost structure must be improved and must be substantially improved if we really want to energize our space propulsion community. So that's the biggest issue, yes. On the other hand, yes, if we can develop a high fidelity design methodologies to improve the situation, then there's a very good chance that we can substantially reduce that 75% cost for our redesign and troubleshooting mode. And that's the only way for us to accomplish our target. And now, the question is this, how to do it? It's always easy to say. I want to share with you a very specific example. Let's take a very powerful stage combustion cycle engine, RD-170, as an example, as shown down here. This is the most powerful rocket engine ever developed in the human community. It's even more powerful than our F1 engine. The thrust level is 1.8 almost 1.8 million pound force, yes. So let's focus on combustor, and then the next thing is this. We should always start with a more advanced design philosophy. By saying that, okay, I mean, we probably should consider a so-called defense in depth approach. So-called defense in depth approach, meaning, okay, this combustion chamber has 331 injectors. Let's make sure each injector can deliver stable combustion. So it's a 100% stable. And then we use other means to provide a design margin. So by doing that, okay, we can substantially reduce the development cost. So in other words, the initial design must be very, very close to the final product. And that's the way to control the cost. Then taking the injector as an example, well, what we have is shown down here, and then this is the injector interior. It has 12 design parameters: the length, the diameter, the location of a kerosene injection port, and so forth. Well, how to do that? If we follow the conventional design methodology, we consider 12 design attributes. Each design attribute has 10 options, 10 parameters. Then combined, we have a huge design space to consider. That's almost mission possible. On the other hand, if we apply the most advanced statistical tools, so-called design of experiment methodology, then we can substantially reduce the design options from that huge number down to 120 design options. So that means, okay, this community must incorporate the most advanced design methodology in order to substantially reduce the design options and also at the same time to reduce the cost, especially for the development. This one shows, okay, the near field of the flame structure. And please pay attention to the scale of the LOX post. The LOX post is very, very small, on the order of 1 millimeter. However, the flame must be anchored within such a spatial domain. So when you look at the rocket engine, it's a mighty device, and the combustor is about 10 inches in diameter. However, the heart of the combustor, the flame stabilization region, is very, very small, on the order of 1 millimeter. Unless we have a full knowledge of the flame stabilization mechanism within such a small spatial domain. Otherwise, the chance for us to design a high-performance stable rocket engine will become wishful thinking, unless we follow the traditional design methodology, trial and error. And if we want to do that, I don't think anybody can afford doing that these days. So this shows, okay, yes, this shows the future. And let me skip this, yes. And yes. So what's the way for us to control the cost? The way for us to control the cost essentially, okay, rely on 3 different things. First one is high fidelity design methodology and more advanced design philosophy using defense in depth approach. This is number 1. Number 2 is, okay, advanced manufacturing and materials. This really offers many, many opportunities. For example, if we can fully utilize recent advances in 3D printing, we probably can reduce the manufacturing cost by a big number. And I was told, okay, if we use 3D manufacturing technique to reproduce IL-10 equivalent rocket engine, we probably can reduce the development cost by a factor of 5. That is a very, very impressive number. And number 3 is, of course, more effective project management. So as I said before, the major problem facing the development of a space launch propulsion system is not on the propulsion concepts or architecture side. It's pretty much on the design side. If we can improve our design methodology, then the chance for us to reach our target and the destination will become much greater. So this is a very, very important message that I'd like to convey with you. And I hope in few years' time, we can totally change this cost structure. And a more reasonable cost structure is probably, okay, for initial design, we spend 10% of the entire budget, 10% of the entire resource. Then for testing, troubleshooting, redesign, and so forth, we probably should control that number down to less than 50%, and that's the future. And then the question is, okay, if we want to develop a kerosene-based stage combustion cycle engine, such as RD-180, how much money is needed for us to accomplish that? I don't have that exact number, but I can promise you it must be substantially lower than F1 engine. That's for sure, probably by at least 1 order of magnitude. That's the future, yes. The second thing that I'd like to share with you is in-space propulsion. Well, for in-space propulsion, there are two, okay, most important things. Number one is, okay, we have to enhance missions by improving the propulsion system performance, durability, cost, and manufacturing. There are good reasons for us to do that. The second thing is we have to develop new capabilities. Well, what's that mean? When we look at, taking our trip to Mars, how much time is needed for us to fly to Mars? Well, this is a summary. Roughly, in the average, the flight time to Mars is anywhere between 150 to 300 days in the average. But keep in mind, that's only a one-way trip. If you want to send a human to orbit Mars or even land onto Mars, you got to consider return trip. Then the return trip will become much, much longer. So there are two practical issues. One, for deep space exploration and even for transportation, there are two issues. Excessive flight time, several hundred days to Mars. Second thing is a limited payload. So those are the two practical issues. And how to solve those problems? Well, let's see. Let's go back to our design table. What are the options? First one is, and again, conventional chemical propulsion systems as we are using nowadays. When you consider the propulsion system, especially the in-space propulsion system for Mars mission, we are still using hydrogen as a monopropellant propulsion system with a very modest ISP and a propulsion performance. So that's option one. Option two, non-chemical propulsion system, such as electric propulsion and others. And also, at the same time, we should not forget about more advanced propulsion concepts, because that may provide solutions perhaps 50 years down the road. Yes. Let's go back to the basics. There's no silver bullet for us to overcome so many issues. So let's go back to our rocket equation. Velocity increment is linearly proportional to ISP, and the vehicle mass ratio, the final mass divided by the initial mass, is inversely proportional to the exponential function of velocity increment. So, well, when we look at the diagram, it shows if we can increase the ISP, say for example, from 350 seconds to 600 seconds, we can increase the payload by a factor of 5. If we can further increase ISP, say 900 seconds, possibly provided by nuclear thermal reactor propulsion systems, then we can increase the payload by a factor of 10. So job number one is, let's try to increase ISP. But how to do it? And again, it's easy to say, but may not be so easy to do it. And again, let's go back to our design table. What are the options? Chemical propulsion systems, two options nowadays. First one is storable hypergolic propulsion systems, for example, hydrogen or bipropellant systems, NTO, nitrogen tetroxide, and MMHD, and so forth. The second one is cryogenic. Let me share some of the recent advances made at NASA Marshall. Lux methane engine is still a viable option for many, many good reasons. And primarily, liquid methane storage temperature is much higher than hydrogen. It's around 110 Kelvin. The oxygen storage temperature is 100 Kelvin, as opposed to 20 Kelvin for hydrogen. So folks can store liquid methane over an extended time period. And also the ISP is better than other fuels except hydrogen, and also the energy density is much better. This is for Lux methane. And also at the same time, people are still considering Lux hydrogen engines. That's another consideration. But my personal feeling is this: we have to do something for propellants. Let's go back to the famous equation for ISP. ISP is linearly proportional to the square root of a temperature, chamber temperature, divided by the molecular weight of the combustion products. So what is the best way to increase the chamber temperature? You got to increase the energy contents of your propellant. Then what are the options? We can use the metallized propellants. It's always an option. Or we can use strained molecules. In other words, those propellant molecules that can be strained in order to store more chemical energy. That's option 2. Or we can always add more energetic components into propellants, so-called functionalized molecules. Then number 4 is use higher energy density ionic liquids, such as HAN and also ADN. In fact, people have already started using HAN to replace hydrogen for space missions. And for example, Aerogel Rocketdyne combined with Air Force Research Laboratory, they launched a vehicle last year using the so-called AFM315E propellant. It's essentially a HAN-based propellant. Well, several reasons. Number 1, hydrogen is way too toxic. HAN-based green propellant is less toxic. It's not zero toxic. It's much less toxic. Density is much higher. ISP is much higher. So that's the right direction for us to move into. However, if we want to substantially increase the propellant energy density, we got to do more than that. Well, this is one option. Taking metal as an example. The nice thing with the metal is the energy density is much higher than conventional liquid propellants. Taking aluminum as an example, the heat of a combustion on volumetric basis is the highest in that table, as shown down here. But that's only for aluminum. What about other metals? Boron actually is a better option. The reason people did not use the boron as a viable propellant option is it's not so easy to ignite boron. But recently, people found a nice way to ignite boron, and also at the same time to substantially increase the combustion efficiency of a boron. So there's a hope there for using metal. Another thing that I'd like to bring your attention is what is the best way for us to use the metal as a fuel? Well, if we want to burn micron-sized aluminum particles, the situation is not very exciting because, 1, the combustion efficiency is not there due to the agglomeration of particles as shown on the right figure. Yes. Oh, I'm sorry. On the left figure. On your side, yes. And on the right, that shows the burning situation of nano-sized particles. So obviously, if we use nano-sized aluminum particles, we can substantially reduce the agglomeration and at the same time to improve combustion efficiency. So the message is, while we are looking for more advanced propulsion systems, let's do not forget about the propellant itself, because that's always a hope there. And let me skip this one. Electric propulsion is wonderful because, the ISP is almost 1 order of magnitude better than conventional chemical propulsion systems. Even for O2 H2 system, the ISP is somewhere around 450 seconds, but the electric propulsion system can easily deliver ISP around 4,000 seconds. So that's always a hope there. And, but the limiting factor is the power supply available for electric propulsion systems. And there are some very encouraging progress made in the past few years. For example, the most recent NASA NEXT project in comparison with the state-of-the-art N-star ion thrusters. And we noticed that the maximum thrust for NEXT thruster is almost 3 times better than the state-of-the-art ion thruster. We are talking about maximum thrust in terms of millinewton. That number is 236 in comparison with a 92 for state-of-the-art ion thruster. And also the maximum ISP for the most advanced electric propulsion system, the ISP is already more than 4,000 seconds in comparison with 3,000 seconds of the state-of-the-art ion thruster. So electric propulsion definitely offers a good direction for us to move into. I hope we can make a more substantial investment into this area. Yes. What about other options such as propellant-less systems? Well, there are 2 options. One is the solar cell. Solar cell. Thrust can be generated by reflecting light. The reason is photons do have energy. Photons do have a momentum, so we can utilize light as to provide the propulsive force. And there are 2 high-profile programs nowadays. The first one is a light sail, sponsored by Interplanetary Society. And the next one is a NASA program, is NEAS, which stands for Near Earth Astronaut Scout. And those are things, good news. Although it doesn't require any propellant, but the thruster level is not very high. But if we have a trip, for which we have unlimited time, those are the good options for us to consider. Yes. Let me just share one photo with you. This is NASA's Near Earth Astronaut Scout program. The spacecraft itself is very, very small. Essentially, it's a CubeSat. But the sail is big. For this particular case, the surface area of the sail is 84 meters square. So it's a huge sail combined with a very small spacecraft. But the futures are quite there. And I am quite optimistic. And this one shows the sail. If you pay attention to the center of the sail, that's the size of the spacecraft. It's getting there, and quite promising. Thermal propulsion, well, if we are really serious about deep space human exploration, we probably would have to consider thermal propulsion systems. 2 options. One is a solar thermal propulsion. Another one is a nuclear thermal propulsion. But for nuclear thermal propulsion, there are several challenges. First one is we have to develop a newer reactor fuel for higher temperature with a minimal erosion, and also we should be concerned with a fission product release and also fuel. Uranium itself is very, very expensive, and we have to overcome that hurdle. And finally, high temperature materials. What is the hope? The hope is the following. Based on the current technology, we should be able to develop a nuclear thermal reactor-based propulsion system with ISP 900 seconds. 900 seconds. What's the payoff? 900-second ISP versus a 300 ISP for a chemical propulsion system. The payoff is we can increase the payload by a factor of 10. So that's quite attractive. One architecture proposed by NASA is shown down here. Well, this nuclear thermal propulsion system has three subsystems, three elements. First one is the core propulsion stage. Then the second one is the inline tank. The third one is a saddle thrust and liquid hydrogen drop tank. By the way, the propellant under consideration is hydrogen. The reason is the molecular weight of hydrogen is very, very small, which in turn can produce a much, much higher ISP. Yes, and that's the situation. Then how to handle that? Well, nuclear thermal reactor is way too heavy. It's way too heavy. Based on this architecture, the system weight is almost 400 metric tons. 400 metric tons. So the way to do it is divide that propulsion system into three components or three subsystems. Each one of them weigh around 100 tons. Then we use SLS, either Block 1 or Block 2 launch vehicles to deliver those three subsystems of a nuclear thermal reactor propulsion system in orbit. Then we put them together and wait for the payload. Then once we get the payload, then we can send the entire spacecraft to deep space, including Mars. So that's the architecture in mind. I have to say that, it's not an easy task, but it offers a good solution. It really offers a good solution if we are really serious about human exploration in deep space, including landing a person on Mars and return that person back to the Earth. There are other propulsion or advanced propulsion technologies with a TRL less than 3. For example, antimatter. People have been talking about the antimatter for years, but the progress is very limited for two reasons. One, it's a really difficult problem. And number two, the resource that we put in has been always modest. Anyway, that's the situation. Beamed energy propulsion, there's a huge community on beamed energy propulsion systems, and electric cell fusion, advanced fusion, and breakthrough propulsions, and all kinds of breakthrough propulsion concepts. And I do encourage people continuing to look into those options. And maybe one of those days, they can provide a solution, not in the near future, but sometime, say, perhaps 20 or even 50 years down the road. Yes. So in summary, I'd like to make a few remarks. For propulsion systems, especially for space transportation and exploration, we should always be concerned with two different types of propulsion systems: launch propulsion and in-space propulsion. Launch propulsion, the single important challenge is the cost, development and the production cost, and also the rate of production. And the only way for us to overcome that hurdle is to apply much more advanced design methodologies and also using the most advanced manufacturing techniques. That's the only hope for us to move into that target. For in-space propulsion, performance still a biggest concern. ISP is not quite there. Because ISP is not quite there, it takes us several hundred days to go to Mars. For return trip, 2 or 3 years' time. That's just not very practical, let alone the payload is very limited. So performance is an issue. And also, at the same time, we should continue developing new technologies and with new capabilities. And with that, I'd like to conclude my talk. I'd really like to thank my friends and colleagues for supporting this presentation. In particular, NASA Marshal, Mark Rogers in the audience. Mark, I really want to thank you one more time for everything that you have done to me. Air Force Office of Scientific Research, and Air Force SMC, Air Force Research Laboratory, Aerojet Rocketdyne, and my colleagues at Georgia Tech. I'd like to thank all of them for supporting this presentation. Thank you so much.